G functions of differential order 2. Thank you very much, Herwig, for organizing this. I'm super happy to be here. I'm just sad I missed the lectures last week. And well, indeed, since I was in Lisbon once and I know the format, so I have some notes so you can see that I prepared the lecture. But I'm happy to improvise depending on what you want to know. Okay, so the title is on G functions of differential order 2. And the new results I'm going to present are joined with Josh Lam and Ichen King. So they are both postdocs in Berlin. But before I get into that, I will explain what G functions are, what differential order 2 means, and why these subjects are interesting, what kind of questions do we ask about them, and so on. Okay, so and I think it's good that I spend some time on G functions because they will play a crucial role in the lectures by Veselin and Junchin later this week. Okay, so let's start with the definition. This is due to Siegel, 1929. So a G function is a power series, it's a formal power series. Let me call it F. So it's a formal power series with algebraic coefficients. This is a Q bar. Q bar is the field of algebraic numbers inside C. And we ask them to satisfy two conditions. So the first one is that they are solution of a differential equation. So we are in the topic of the workshop. So there exists a non-zero differential operator L with algebraic coefficients. And I'm going to use this notation for differential operators in one variable, just to emphasize that the multiplication by Z and derivation with respect to Z do not commute, so I use these brackets. So there exists a differential operator such that when you apply to the power series, you get 0. And first remark is that, well, this is L is something of the form C G Z derivative with respect to Z to the power J. So if you apply to F and you say that it is equal to 0, you get a recurrence for the coefficients with polynomial coefficients. And then this immediately implies that even if I ask the coefficients to be in Q bar, they actually lie in a number field. And the notion of differential order I'm using here is the order. So if CR is different from 0, then this is called a differential operator for the R. And the differential order is the minimal order of such a differential operator. Yeah, they are all homogeneous. So for J equals 0, this is multiplication of the function by the polynomial. Yeah. I can write for homogeneous if you want. that all L of these form are homogeneous. Okay, that's the first condition. So these are holonomic power series. And the second condition is about the growth of the coefficients. And the condition is that there exists a real number C, strictly positive, such that, well, two things. So first thing, you would like to say that the ANs are in absolute value at most C to the N. But these are algebraic numbers, so it is always more reasonable to ask this property not only for the ANs, but also for all the Galois conjugates. What I'm going to ask is that if you apply an automorphism, so you consider all Galois conjugates of the AN, then all the absolute values are bounded by C to the N. And the consequence for this is that if you consider the power series AN set to the N, or more generally, the one given by applying sigma to the coefficients AN, this has strictly positive radius of convergence. Radius of convergence is strictly positive. So these are actually series that we can evaluate at sufficiently small complex numbers. This is the first condition. And the motivations of Siegel were of arithmetic nature, so he wanted to prove irrationality, transcendence results about the special values of G functions, and we will see a great breakthrough in this direction later in the week, using G functions to get these results. And this is not enough, because you cannot distinguish a very small number with a huge denominator from the same one with a small denominator. So there's a second condition, which is more of an arithmetic nature, which is a condition about the denominators. Okay, so we look for the first coefficients, A1, AN, and we want the denominator, the common denominator, to be at most C to the N. Okay. So what does this mean? Does it mean common denominator? If these are rational numbers, it's literally the common denominator. And otherwise, these are algebraic numbers. It means there exists an integer such that if you multiply by this integer, you get an algebraic integer, and it's the smallest one. So this is the smallest. Dn is an integer such that dn A0 up to dn A1 up to dn AN are algebraic integers. Okay. So that's the definition of a G function. Questions, complaints, interruptions? Good. You can do A0, you can do A1 is the same. Usually, yeah. So maybe let me say this is for all n, and usually I start with 1 because if you do C to the 0 is 1, and then it is not necessarily true, but because it doesn't matter. You can start with 0. Okay, so let me give you some examples. So the trivial example is polynomials with algebraic coefficients. And if we get rid of this example, here the condition is that the radius of convergence is strictly positive. And in general, so unless a polynomial, the radius of convergence is finite. Okay, so these operators L in general, they will have, well, essentially always, they have singularities at finite distance, and then the series will converge up to the first singularity. Second example, if you take a, yes? The example is polynomials. Yes, I'm saying if you take a polynomial with algebraic coefficients, that is trivially an example of this. In that case, the radius of convergence is infinite. And if you are not a polynomial, then it's finite. Is it better? Okay, second example, if you take all an equal to 1, then this is also quite a trivial example. And you get the geometric series. And then this is what explains the letter G in the definition. Okay, so for Siegel, this is a generalization of the geometric series. But a bit later, I'm going to give another possible interpretation of the letter G, which is maybe more interesting. Another example are algebraic power series. So if you take a power series with sorry, algebraic coefficients, and you assume that it is algebraic over the field of rational functions in one variable, then it is a G function. And so showing the existence of a differential equation and of this condition is well, not that hard. It's maybe more classical. And the arithmetic content is this condition on the denominators. And this is a theorem of Einstein. It's a theorem that really opens something new in the topic. And in this case, we even get some stronger conditions, which is called globally bounded, which means that if you actually if you replace the variable here by an integer multiple, then you get algebraic integer coefficients. So it's a bit stronger, or much stronger. And third example is given by hypergeometric series. So EP minus 1, A1 AP, A1 BP minus 1. Okay, so let me write down the formula and then I'll tell you how to think about them. There's an n factorial in the denominator, and then the general term is a quotient of Pohammer symbols of the A's and the B's. Where Pohammer symbol is a generalization of the factorial. So actually this n factorial should be understood as the Pohammer of 1. And if you think in these terms, there are actually as many A's as B's. And the condition is that the A's are rational numbers, and the B's are rational numbers which are not negative integers. Otherwise, you will be divided by 0. So this is the classical formula for the hypergeometric series. And so how to think about them maybe in more conceptual terms. So these are power series with the property that, so you look at the coefficients an, and you look at the quotient of two successive coefficients. So you do an plus 1 divided by an. And the property is that this is a rational function of n. So you can write this as a quotient of two polynomials. And the important condition for to be a G function is that these two polynomials have the same degree. And this degree is the P. So from this, so this is a recurrence relation for the coefficients, very simple. For this, from this, you get the differential equation. Then this condition is, again, not hard to check. And this is a bit more interesting. For the denominators, you need to, so this was done by Siegel. You need to estimate a little bit the coefficients there. And then what you use is that the least common multiple of 1 up to n is for example, at most 3 to the power n. Okay? So if you want, this is a weak form of the prime number theorem. Okay? So let me give you an example inside the example, and then this will allow me to do the transition to the other meaning of the letter G. So this is like most classical example is so a hypergeometric function where P is equal to 2, and then the parameters are 1/2, 1/2, 1. And in this particular case, if you work out what the quotients of Pohammer are, you can write the series in terms of binomial coefficients. And the coefficients is n, choose among 2n to the square. And then you divide by 16. So this is a solution of a differential operator for the 2, and 2 is the minimal order. It has this shape. The singularities have 0, 1, infinity. And this function is given as a power series, but there is also an integral representation. And then this is going to be fundamental for the rest of the story. So it is also equal. It's an integral depending on the parameter set. And what you integrate is, so is this elliptic integral. You integrate 1 over square root of this function, except that if you do z equals to 0, then here you find this integral, and here you find 1. Okay, so it cannot be literally equal. You need to divide by the value of this integral. The value of this integral is pi. So actually, the correct formula is 1 over pi times this. This will come back again. It's quite important. And when you see this integral, what you want to think is that this function, this hypergeometric function, comes from geometry, in the sense that it is a period function for a family of algebraic varieties, in this case, a family of curves. So it's the usual trick. Well, this is not a rational function, so you introduce a new variable y, which is going to be this square root. So then y squared is x times 1 minus x times 1 minus zx. And then if z is a complex number which is not 0 or 1, then this is an elliptic curve. This cycle is a class in the homology of this elliptic curve, and then this is the holomorphic differential. So you are relating this function to periods on this family of curves. And for example, the fact that this is a differential equation of order 2 is related to the fact that on an elliptic curve there are two homology classes which are linearly independent. So you compute the derivative 1, you go under the integral sign, this gives a new class, and when you compute it twice, you have 3 classes, so there has to be a relation, and this relation is the differential equation. Okay, so what is the general picture? So the general picture is as follows. So we have some space of parameters S, which is inside the affine line. Is where the coordinate set lives. And we consider a family of smooth projective varieties over S. Well, it's pi. So this is a family of smooth projective varieties. And then associated to this family, there is the Gauss-Manning connection. So what is this? You consider H J the RAM X over S. Okay, so this is a vector bundle on S, and the fiber is the vector bundle with fiber, the RAM homology of H of XS. Okay. So you put together all the RAM homologies of the fibers, and then, as in this example, you can differentiate homology classes with respect to the variable set, and this gives a connection on this vector bundle, which is called the Gauss-Manning connection. Okay. So this is a general construction what you can do for every such family over any basis. But the advantage here is that this is one-dimensional. It's inside A1. It comes with a coordinate Z. So actually, this vector bundle is trivial. So it's just isomorphic to OS number of copies. So the connection is just a matrix of differential forms. And then you can use the usual thing. You can choose a cyclic vector for this matrix. And then out of this, you get a differential operator. So not in a very canonical way, but there's a way to get differential operators. Which are usually called Picard-Fuchs. So my understanding is that you usually use the terminology Gauss-Manning for the point of view of vector bundles with connection, and then Picard-Fuchs for the differential operators that you can get out of them. And more precisely, what we are going to call a Picard-Fuchs is actually for every family of smooth projective varieties, you get such an operator. Then you can factor it inside this ring of differential operators, and then you can recombine the irreducible factors. So a Picard-Fuchs will be a product of irreducible factors of Picard-Fuchs operator associated to families. So in the more geometric point of view, it means that you can take sub-quotients of Gauss-Manning connections, and then you can take extensions of sub-quotients of Gauss-Manning connections. Okay, so yeah, I guess that's good. So then let me give you a theorem and a conjecture. So the theorem by André is that every solution in algebraic power series with algebraic coefficients of a Picard-Fuchs differential operator is a G function. Okay, so this gives a very rich family of G functions coming from geometry. And well, the concrete, yeah, let me say something about the concrete meaning of this statement. So we have the water system now. Yeah, so concretely, what this means is that if you consider a period function so period functions means you have such a family of varieties. You okay, let's let's say 0 is a smooth point to simplify a little bit. So you look at the neighborhood of 0, and then you consider a section of this vector bundle. It means a family of differential forms indexed by the parameter. And locally around this point, you have cycles to integrate that are constant. So this gives some functions of the shape integral of omega z on sigma. And okay, so the statement more or less means that this is a G function. But of course, it is not true because we already see in this example here that you don't get a G function. It doesn't have algebraic coefficients. What you get is pi times a G function. So this is something you need to take care of. All period functions are C linear combinations of G functions. And you can be more precise here. The coefficients are actually periods of the family. Yes, exactly. So this is, thank you. So there are two issues. First one about coefficients. And this is the easiest situation where you suppose this is if Z is a smooth point, 0 is a smooth point. Okay, so it means really the fiber at 0 is a smooth projective variety as well. or the differential equation does not have a singularity at 0. But this is not what happens in general. We already see in this example. In this example, 0 is a singularity. And in that case, some solutions will maybe be power series, but some others have monodromy. So the general statement is, in general, what you get is C linear combinations of C to the A log Z to the B and power series. So this is a G function. And the monodrome is quasi-unipotent, which means that A is a rational number, B is a positive integer. Other questions? Okay, so that was the theorem. And then the conjecture, which is called the Bombieri-Duor conjecture. So it's usually stated with the slogan, all G functions come from geometry. And this will be a second possible meaning of the letter G, geometry. And if you want something more precise, a way to make it more precise is that every G function is annihilated by a Picard-Fuchs differential operator. So among the differential equations that enter the definition, not on the blackboard anymore, one can always find one which is a product of irreducible factors of things coming from families of smooth projective varieties. Yeah, so it's extremely open. It is true for G functions of differential order 1. And that's it, pretty much. But what we know is that you take a G function, you take a differential equation of minimal order, and we know, for example, that it shares many of the properties of Picard-Fuchs differential operator. So this kind of thing. So the monodrome is quasi-unipotent. P curvatures are nilpotent outside a finite set. So there's some evidence that this could be true, but already for G functions of order 2 is very, very, very open. Okay, and maybe to end this part, let me tell you that this the theorem of André and the conjecture of Bombieri-Duor suggest that the special values of G functions, so special values means values at algebraic numbers inside the radius of convergence, inside the disk of convergence. The set of these numbers, which is actually a ring, could be equal to the set of periods. It may be called P periods. So effective periods to be precise. So this is not quite true because 1 over pi is actually a special value of a G function. So you need to consider at least periods divided by powers of pi. And yeah, so once you do this, this is a conjecture that these two things are equal. And then this is maybe another reason to to get interested in G functions. So this could be a way to prove transcendence results about periods. So here the difficult thing and the interesting thing, like in conjecture as opposed to theorem, is you start with a G function, you take the special value, you would like to know that this is a period divided by pi. And we know how to prove the other inclusion is known. So this is something I observed maybe last year. It's not hard once you know how to represent periods. Okay. Any questions? Now I'm going to state a new theorem. Okay, so the theorem is with George Lamb, is that there exist actually many G functions coming from geometry of differential order 2. This is true, but it's not the interesting part of the theorem. That are not polynomials in the following function. So here you get, so these hypergeometric Cs are a rich family of examples of G functions. We also have algebraic functions here in the blackboard before. And you can combine them in two ways. First of all, you can make an algebraic substitution of the variable, so you can replace Z by lambda Z for an algebraic function Z, as long as it's defined at 0. And you can also multiply by algebraic functions. So you can consider all functions of this shape. So algebraic function times hypergeometric series evaluated at an algebraic function. Product sums of G functions are still G functions. So you get a big supply of G functions this way, and the statement is that these do not cover all G functions, and there are already many examples of differential order 2 coming from geometry which are not of this shape. Lambda 0 is equal to 0. Lambda 0 is yes. Yes, I want something like Z. I want that the thing starts. Exactly, yeah. It's not very important. You can set the G functions at other points of the. Okay, is the statement clear? Yes. Well, finite is not many. So so what actually means is that okay. So if you look at the differential equation, this corresponds to a local system on P1 minus some points, and there are infinitely many such local systems, and they are not obtained from each other by reparametrization of P1. This is what it means. Yeah, in terms of the functions, it's not super clear what this means, but okay. So maybe a few remarks. First one is that this is the 2 is the minimal order. 2 is the minimal possible order. Because a G function of differential order 1 is actually algebraic. And one way to see this is using these properties of the minimal differential equation I mentioned. So the minimal differential equation of a G function has regular singularities and quasi-unipotent monodromy. So if you write a differential operator for the 1 with this property, and you write down a solution, then you'll see that it is algebraic, especially because of the property that the exponents are rational. Okay, so 2 is the minimal order. This can be made very explicit. So it's not an abstract existence result, so explicit examples. For example, you can take the polynomial z minus 1, z minus 2, z minus 82, not? And you can consider the differential equation of order 2 with this leading coefficient, and then this p prime over 2, and then plus z minus 10 divided by 18. And any solution in a Q bar Z of this is an example. Reducible to? I think it's a Lamé equation. In the books about special functions, this is called a Lamé equation, I think. I don't claim anything, I think. What is minimal is the number of singularities. So there are no examples with 3 singularities, but this is just an example. I will maybe tell you how it is produced. Okay, that was the second remark. Maybe let me tell you where this question comes from. I don't have a closed formula for the solution, so you can write down the first coefficients, and the denominators are already quite big. And yeah, I mean, I know it comes from geometry, so this is actually related to, yeah, so it comes from a Shimura curve, so it is, maybe it's not super explicit because you have a family of abelian varieties with multiplication by a quaternion algebra, and then, but the cohomology is quite big, so you cut it into a piece of degree 2, and then there's some differential forms that you can integrate on some cycles, and you get this thing. But I don't know of an explicit formula. There are, yeah, so maybe let me mention a bit of previous work. So this answers a question of Fischler and Riboal. The theorem, yeah. The question they ask is, do there exist G functions which are not polynomials? So this is maybe 2020, and this was motivated by a similar question by Siegel in his original paper for E functions. And now we know, so this is something I proved with Peter Jossen, we know that there exist E functions of differential order 3, and 3 is the minimal possible, which are not polynomials in hypergeometric series. And there you have much less flexibility. You cannot multiply by an algebraic function is an E function if and only if it is a polynomial. So you cannot multiply here, and then you cannot really do anything to the variable except multiplying by a constant. Okay, so they ask this question, and well, it was clear from their paper and clear from my work with Peter that the answer should be no. But there was this interesting thing that it's supposed to start in differential order 2 as opposed to 3. And it's also, in some sense, harder because you have, so what we did with Peter was an analysis of the singularities of the Fourier transform of the differential equation. And here, these algebraic functions, they completely mess up the singularity. So you cannot really get anything from the singularity. So motivation was to, well, to understand a bit why order 2, and then to go beyond the technique of the singularities. Let me mention 2 other results. So there's a paper by Dreyfus, Riboal earlier this year, where they they have a variant of this kind of question. So they want to know which solutions of differential equations are polynomials with algebraic coefficients of solutions of differential equation with a given number of singularities. You start with 3 singularities, for example. Can we represent everything as polynomials with algebraic coefficients in solutions of 3 singularities? And they prove that the answer is no. And using this kind of technique, you get a variant of this question, but only for result for lambda rational, as opposed to algebraic and denominator of bounded degree. It's not a mistake. It's just my handwriting. So there is a no there. Can you see it? Yeah, sorry. With the denominator of bounded degree. And there's another related paper, so this is probably the hardest moment of the talk. So, but we have some Dutch people in the audience, so that maybe can help me. And I will use capital letters. It's an E, sorry. A J. How do you pronounce that? Oui. Okay. And then Vadim, this is easier. Duco. Okay, so they have a paper from last year, which in connection to what I'm telling, they look at some particular local system of order 2, which actually we realize it's an example of one of these infinitely many. And in that case, they can write down explicit integral representation of such functions. And they suggest very strongly that it is not of this shape. And I think putting the two things together, we can actually prove that it is not of this shape. Oh, it's 22. So now I can do two things depending on the audience. So I can either tell you something about the proof, or maybe tell you something more about this analog for the E functions. What do you prefer? Even better. But I think even with 15 minutes, I cannot do both. The proof, yeah, great. Okay. This is 2020. Okay, so some ideas of the proof. So it's maybe in 4 steps. The beginning is a bit similar to what we had done before with E functions. And yeah, so maybe step 1 can be summarized with the slogan that functions are complicated, Tanakian categories are easy. So the first step is to reformulate everything in terms of differential equations. And maybe here by differential equation, what I mean is modules over this ring of differential operators. Sorry? Reformulate means, so the question is every G function of this shape? And I will give an equivalent version of the question where we don't talk about functions, we talk about differential equations. Thank you. Yeah, so you will notice there's a subtle difference with the previous notation. So before the coefficients were polynomials, now the coefficients are rational functions. And this is related to the fact that we need to control all the singularities of all these algebraic functions. So we need to shrink every time the open of the affine line. So it's like working in terms of the modules, it's like working at the generic point. Okay, so you work with local systems, but your open is smaller and smaller. Okay, so there will be two categories of such things. One is differential equations of G functions coming from geometry. So we'll have two such things. One is going to be called H, the other is J. So these are Picard-Fuchs differential operators. So I look at the category of all modules associated to Picard-Fuchs differential operators. And the important thing here is that this has a tensor product. You can do the tensor product of two such modules, and it is again in the category. And with respect to this, it forms a Tanakian category. This is one of the points which is not so clear what it does on the differential operator itself, so it's better to work with modules. So the idea, this will be the differential equations of all G functions coming from geometry, and inside, I'm going to look at the differential equations of these kind of functions, and then the reformulation will be to show that this inclusion is not an equality. Okay? So here this is generated by, okay, so we need to find a family of differential equations that annihilates all these functions. So it depends. You can take solutions as a fiber factor, and this is maybe the best thing because we want to compare with the yeah yeah, the generic point. And in that way, you can compare with the differential Galois group. Over Q bar. The fiber factor, you look at the Q bar vector space generated by basis of solutions. The important thing of the use of Tanakian categories here is that at the end, the Tanakian groups will be the usual differential Galois groups of the differential operator. The Galois group, the Tanakian fundamental group will be the differential Galois group of the operator. So actually, every module over this ring is cyclic. So you can actually take a differential operator generating it, and in such a way, what you get here as from the Tanakian formation is the differential Galois group in the usual sense of that differential operator. Okay, so yeah, what do we do? So yeah, I'm doing H now. So H has two kind of things. So it has algebraic functions. So we need modules with finite monodromy. Okay, this will correspond to the differential equations of algebraic functions. And we also have the usual hypergeometric differential equations, but because of the algebraic function here, one needs to be a bit more careful. So what we do is we have a curve with two ramified covers to P1. And on P1, we take a hypergeometric differential operator, and then we pull it back by one of the maps. So this is the analog of making the substitution of the algebraic variable, and then we put it back again to with the other one to still have something on P1. Okay, so this is a hypergeometric differential operator. Okay. So, and the main point is that every function of in the theorem is a solution of an object in H. Okay, so essentially what we need to do is that, so now we need to find an object of dimension 2 of H, of G, which is not in H. If it is countable, yeah, I guess it has countably many generators, yeah. But G also, so. Yeah. Okay. Is that more or less clear what I'm trying to do? So step 2, and yeah, so step 2 deals with the following problem: is that we need to take polynomials. Okay, it's not just about not being equal on the nodes to such a function. So take polynomials here correspond to taking tensor products of the differential equations somehow. And yeah, so step 2 is, so this uses in a fundamental way the work by Boykers and Heckman. Yeah. Yeah, in the situation of the function of the theorem, yes, but here I take the more general situation. and you work with this notion of G functions with monodromy, so you allow powers of set and logs. So they have this beautiful paper where they compute the differential Galois groups of hypergeometric operators. And using their work, this step 2 shows that if an object of dimension 2 of G is in H, then, okay, so being in H means that you take finitely many such things. You take products, tensor products in all possible ways. You take subquotients, you maybe take extensions, and at the end you get the object. So it's in principle a very complicated operation. And using this fundamental piece of differential Galois theory, what we show in this step is that if an object of dimension 2 is in H, and here you need with differential Galois group SL2, then it is actually generated by a single one of these objects. Then it is generated by a single pi to lower star pi and upper star of H, and important with H of order 2. So H of order 2 means this is the classical, the most classical differential operator, the one by Gauss, and you just need one of those. Okay. And then you are in a much better shape to find something that is characteristic of these objects. And this is the this is the new ingredient with respect to previous things. So step 4, step 3. So we look at age. Maybe, yeah, so we another an object of dimension 2 of G. So this gives rise to a local system on some open of P1. Yes? Yeah, I mean, SL2C or SL2Q bar. Depends what you are doing, yeah. Yeah, the differential group is SL2 seen as an algebraic group over Q bar. Yeah, thank you. This one is SL2 of C. So yeah, so an object of dimension 2, so it's a local system on an open. You look it as a representation, and the invariant we are going to consider is the trace field. What is the trace field? So the trace field is the field generated over Q by the traces of the representation applied to all elements gamma of the fundamental group. And well, let me not emphasize this too much, but for some reason, it's better to look at the adjoint trace field, which means here instead of rho, you put the adjoint representation. And then this has a bit of better properties. And then the key. Yeah, thank you. Yeah, so you look at traces of all elements of the fundamental group acting on the space. And then the key point is that for objects of H, this trace field is contained in a cyclotomic field. So in particular, it is abelian. So this is the argument is beautiful. It follows from Katz's rigidity theorem. So this uses Katz's rigidity theorem. So rigidity means here you look at each element in the fundamental group. It corresponds to a matrix. And rigidity means that if you know the conjugacy classes of these matrices, you completely know the representation. Okay? So knowing the conjugacy classes means that you can conjugate every image by a matrix, but these metrics can be different for different elements. So rigidity is a situation where if you can conjugate each one by an a priori different element, actually you can conjugate all of them by a global element. So the representations are isomorphic. And using this, so Katz tells you that hypergeometric things are rigid, and then this means they are determined by their local monodromies. But these are in the cyclotomic field because the alphas and the betas are rational, and they essentially give you the exponents. Okay, so you are here. What we need is to find an object of dimension 2 of G with non-abelian trace field. The reason why you need this adjoint is to take care of these pi's. And the adjoint has the property that it is invariant when you pass to a finite index subgroup of your fundamental group. Okay, so step 4. I can stop at any moment. For example, now. So let me just say step 4: find non-abelian trace field. And this is where Shimura curves enter, because Shimura curves are associated to totally real number fields, and then they come with natural local systems, and their trace field is the totally real field. So you need to go through the tables and then find a Shimura curve with non-abelian trace field, and you can take, for example, F to be a totally real cubic with discriminant 148, and a cubic field has a Galois group either is Galois and the Galois group is Z mod 3, or it is not Galois and the Galois group of the closure is S3. So we want this case. So how do you distinguish them? You distinguish by the discriminant is a square or is not a square, and 148 is not a square. So we are in this case. So you get your Shimura curve. You get your local system, and then this is an equation that works out explicitly the uniformization of this thing. Okay, that's it. Thank you.